Welcome to yet another episode of our current electricity. Now, today our subtopic, we are going to look at potential difference and the electromotive force. Remember we said electricity is the flow of charged particles. Now, here I want to look at how do we get electricity. You can get electricity we can get electricity when we have potential difference or when we have electromotive force. Now, what is the potential difference? Here we are looking at the work done in joules when one coulomb, remember we looked at a charge, one coulomb of electricity moves from one point to another. In other words, when charge moves from one point to another, work is done, and we say that work done is known as potential difference. We get it from this equation here, where we say work done equals to charge times PD, where we've said W is work done, Q is charge, V is PD. So the definition is got from this equation, which is derived from this one, that the V, which is potential difference, is equal to work done over charge. So we are saying that PD is the work done, when 1 joule, it's the work done in joules when one coulomb of electricity moves from one point to another. Okay, that is the PD. Then when we look at EMF and PD are related, although PD we look at work done to move from, example, I can have a point A, then I also have point B. Then it means that if A and B are at different potentials, then there is a PD between the two. So the work done to move charge from point A to point B, we call it PD, and it can be abbreviated as VAB. PD between A and B, that is what we call potential difference. Okay, when we talk about EMF we say total work done in joules per coulomb of electricity conveyed in a circuit in which the cell is connected. We look at this basically. We shall be able to explain EMF and differentiate it from PD. Now, when we look at this circuit here, we say we have a cell of EMF E, and then we connect it to a battery of resistance RCD, and then we connect it also to a resistor of resistance RAB. Now, when electricity moves, remember it moves from positive, it goes through this resistor, and then it goes through the bulb, and then finally it goes back to the circuit. Now, when we say EMF will be now the total work done. In other words, the summation of this PD here and this PD here. If there is internal resistance, also we also add up the EMF. We also add up the PD across the internal resistance, and therefore that's why we say it is the total work done. Remember we said work done to move when a coulomb of charge moves from one point to another is PD. So we say if we look at the work done here and we add up to the work done here, if there is internal resistance, we also add up the work done due to internal resistance, then the total work done altogether gives us what we call the EMF. In other words, EMF is summation of the individual PDs within a circuit. Now, we move ahead. We are saying PD can be between AB or CD. Like this resistor, we can talk about EMF, we can talk about PD between AB. We can also talk about PD between CD. This is what we are talking about. And PD between AB, we are calling it VAB. That is PD across resistor RAB. PD between CD, we are calling it VCD. That is the PD across resistor RCD. Now, when we sum it up, we get what we call EMF of the cell. Like PD, EMF both have the SI unit known as volt. Volt is abbreviated as V. Between AB, current finds resistance RAB, and between CD, current finds resistance RCD. I've already explained that one earlier. But now we are saying that what is then resistance? We are talking about resistance. Resistance is the opposition to the flow of current. Remember, we said current means flow of charge. Now, when the flow of charge is resisted, then we get what we call resistance. Resistance is the opposition to the flow of electricity, or flow of charge, or flow of current. So resistance is having an SI unit of ohm. And from ohm, we get what we call Ohm's law. Ohm's law looks at the relationship between PD and current. It looks at the relationship between PD and current. And Ohm derived this statement that says that if current is flowing through a conductor at a constant temperature, then the potential difference is directly proportional to the current, provided the temperature is constant. We are saying that Ohm's law states that the current flowing through a conductor at a constant temperature is directly proportional to the potential difference between the ends. And now we are saying that current potential difference is proportional to current if the temperature is constant for all ohmic conductors that obeys this law. This is true. Now we are saying V equals IR. Remember, here we had V is proportional to R. If we introduce equal signs, then V will equal to, put a constant, we are calling it R times I. So it means that R is the constant of this equation. So R will be the resistance, and it is constant provided the temperature is kept constant. So we have said there is a relationship between current and PD. Current flowing is always proportional to the PD, provided the resistance remains the same. And resistance will remain the same only if the temperature remains the same. Okay, let us look at calculations in circuit diagrams. When we look at our circuit diagram, we have resistors. We have already looked at resistors earlier. We have a cell which will give us our EMF, or to give us our PD, and then we have current flowing. Of course, flows from always positive and goes to the negative. Now, when we are looking at calculations, we look at the first thing: identify the arrangement of resistors. Resistors can be in parallel arrangement or series arrangement. Let's consider series arrangement as the first one. Okay, we have a circuit below. Now, current always comes from positive and ends with the negative. If current is flowing from R1, then R2, and finally R3, then to the source, then it means that the same current I is going through this one, after goes through that one, after it goes through that one. Then it means that since they have the same current, R1, R2, R3, R1, R2, R3 have the same current flowing through them, then it means they are in series. So series arrangement is when resistors have the same current flowing through them. Now, this means that I through R1 is the same as I through R2 is the same as I through R3. Okay. Now, in order to get the total resistance, to combine to get the overall resistance, then it means that we shall say our total resistance is just a summation of R1 plus R2 plus R3, and you get our total resistance for series arrangement. Remember, I've said for you to identify that these resistors are in series, look at how current flows. If current is the same, then those resistors are in series. And to get the combined resistance, then you just add them up. Okay? We have already said that is because current is the same. Now, for series arrangement, there is something else to note, that PD is different. PD is different. Let us look at an example here. Now, we consider the circuit. This time we are given the figures. We have R1 of 2 ohms, R2 of 3 ohms, R3 of 4 ohms. They are saying that find the total resistance in the circuit. If you are going to get total resistance in the circuit, step 1, identify the direction of current. Current is from positive, moves through this R1, then the same current will go through R2, then it goes through R3, and it goes back to the source. Then that means that R1, R2, R3 are in series. We'll go back to how we got, we'll go back to the formula of how we get the total resistance in a series. We say total resistance in series is just a summation of R1, R2, R3. So it means that we shall get R1, substitute, put 2 for R1, put 3 for R2, put 4. Add them up, we get 9 ohms. As simple as that. So when you are given resistors in series, add them up, get the total resistance. Then we look at parallel arrangement. How do you know that resistors are arranged in parallel? Resistors are said to be in parallel if current flowing through them separates. In other words, if we consider the circuit below, current comes from positive, it moves, this is our total current. When it reaches the junction here, it separates into I1 and I2. Now, when it separates into I1 and I2, then it means that R1 and R2 have separate current. They share current. Therefore, they are in parallel. So because current separates, then R1 and R2 are in parallel. So we say those ones are in parallel. The other common thing here we need to put into consideration is that these resistors in parallel have the same PD. The PD across R1 is the same PD across R2, and is the same PD when you combine everything in parallel. It's the same PD. That one you should know it. Like I said, For resistors in series, current is the same, PD is different. Here, resistors in parallel, current is different, PD is the same. That one you need to know. Here we have said R1 and R2 are said to be in parallel because current separates. Therefore, total resistance R is obtained from this formula. We shall say, to get our R, we say 1 over R equals to 1 over R1 plus 1 over R2. 1 over R, remember you want R, equals to 1 over R1 plus 1 over R2. This is how we get our R. Okay, note. Yeah, there is a note important. Resistors in parallel have the same PD but different current. Okay, we'll stop. Okay, let us look at the example where we have resistors in parallel. Okay, now we are saying we have the circuit diagram. The moment you want to identify resistors in parallel, first show the direction of current. That is step 1. Current comes from the longer terminal is the positive terminal and the shorter terminal is the negative terminal. It goes from positive, then when it reaches here, it separates. And part of the current I1 goes through R1 and part of the current I2 goes through R2. Then later it is going to be combined and you get back your I, which started here. So the moment you see that these resistors have different current, shared current, or current which are separated, then R1 and R2 are said to be in parallel. Now, then you say, if that is true, then our total resistance is obtained from this formula, that 1 over R equals to 1 over R1 plus 1 over R2. Remember, our total resistance, we are calling it R. We don't get it directly, but we shall get the reciprocal. Now, so we are saying, if we are given R1 to be 1 ohm and R2 to be 2 ohms, when we substitute in the formula above, we shall say 1 over R equals to 1 over R1, which we are saying it is 1, plus 1 over R2, which we are saying is 2. Then when we solve, get the LCM, here we have 2 divided by 1, you get 2, then 2 divided by 2, you get 1, and then we shall have 3 over 2. Then to get R alone, we shall get the reciprocal. What was down is up and what was up is down. So we shall get this answer as 0.67. This is our calculation. Okay, pause.